This is part 3 of the thermochemistry notes. We're going to be talking about calorimetry. And calorimetry, as I have shown up there, is the accurate and precise measurement of heat changes for a chemical or physical process. And a calorimeter is a device for measuring heat. So let's take a look at a what's called a coffee cup calorimeter. I'm going to draw a little picture. This is just going to be a styrofoam cup, you know, like you get coffee from if you go to, let's say, 7-Eleven or someplace like that. So you've got your coffee cup, which is styrofoam. And then inside, you're going to have your sample of whatever it is that you're going to be looking at. Could be a chemical reaction, could be a piece of metal that you want to cool off in some water and see how much heat it releases. And then you're also going to have a thermometer. So that's a thermometer there. So what you're going to have as the sample gives out heat, the water temperature changes. So as the sample absorbs or releases heat, the water temperature changes. So what we're going to do is measure the amount of water change. And we're going to use the Q equals mc delta T equation for water, because we know C for water. That's known. We're going to measure the delta T using a thermometer, so that we're going to measure. And we know the mass of water. Let's just write of water. We can measure that before we put it into our styrofoam coffee cup. So all that we will know. And then what we're going to end up doing is down here, this Q, we're going to calculate. Once we know the Q for what went on with the water, then we also know the Q for what went on with the sample. Because by the law of conservation of energy, whatever energy is lost by the system has to be absorbed by the surroundings. So we're going to make the assumption this is a closed system, so that all of the heat lost or gained by the sample will be transferred to the water. So this actually ends up being calculated, let's put a D in there, calculated for sample. Because once we know it for the water, all we do is change the sign for the sample. Now let's take a look at heat changes as we go through phase changes. And we're going to draw a little diagram here. As we heat up a solid and we convert it to a liquid, this has the term melting that we use just in day-to-day usage. But the term that scientists use is fusion. So when we melt a sample, we fuse a sample. Once we have it to the liquid form, if we keep heating it up, we'll completely vaporize the thing. So this is vaporization. Now with both of these, we have to put heat in. So this whole direction here, we are putting in heat. So this is all an endothermic direction. So melting and vaporizing are endothermic processes. Now let's say we've heated it up to the gas and then we decide, okay, we want to cool it down. So now we're going to cool it down. So we cool it down and we cool it down and we cool it down. And what happens is it condenses, condensation. to become a liquid. If we continue to cool it down, we can solidify it again. And so this is called solidification. Now you and I, in common usage, call it freezing, but its scientific term is solidification. This is a little animation of a calorimeter that I thought might be a little more easier for you to see. This shows a sample chamber that has reactants in it. This has the water. This you've got to have a stir going on because you want to keep the water circulating so that the water is the same temperature throughout this chamber. So as the reactants either absorb or release heat, they're going to heat up the water, and the water in turn is going to heat up the thermometer, and then we can use that Q equals mc delta T to solve the equation. Here's another way of looking at changes that occur in temperature and energy as we're changing states. And we're going to look at here at a heat curve for water. On this axis, we're going to have degrees Celsius. So let's just go ahead and label that. That's degrees Celsius. And I'm going to go across straight here, right across from this line, and I'm going to label that 0 degrees. And then straight across from this line, as much as possible, I'm going to label this 100. And let's take a look at what's going on. This region right down here, and let's say this is minus about 100, because that looks about right. If we're talking about water, until we get to 0 degrees Celsius, the water is going to be in the solid phase. So draw a line straight on down, and all of this is in the solid phase. If we were to draw the water molecules, what we would see is they would all be locked into position. They'd be locked into a crystal. So here we are changing the temperature of ice. Once we get to 0 degrees C, the ice begins to melt. Or, as us scientists like to say, it is undergoing fusion. So this whole region here, we are continuing to put in energy, and I forgot to label that. That would be joules going across. So we are putting in energy. You can think of this as putting water in a frying pan on the stove and then turning the burner on, and the burner is putting energy into the water sample. So we've melted the water sample, we've gotten it to 0 degrees Celsius. And what's going on here is fusion or melting. So let's take a look at what's going on in this region. Here, we begin with solid, and we're just beginning to melt. And at the end of this time, we have pure liquid. So we have solid and liquid phases present as we're going through the fusion process. So this, we would have some solid floating around. And then we'd also have just some looser water molecules starting to slide past each other. So very organized, and then some water molecules starting to slide past each other. Once everything is melted, we will be at 0 degrees Celsius. And now the water will actually start to warm up. And it will continue to warm up. The water will get hotter and hotter until we reach 100 degrees Celsius. So let's draw another line straight down here. So all through this region, we have pure liquid. Once we get to 0 degrees, or to 100 degrees Celsius, and all of the water has reached 100 degrees Celsius, then we begin to turn the water into gas. And this is vaporization. So this whole horizontal straight line here represents vaporization. So let's draw another straight line down. In this area here, we have liquid and gas phase present. So we will continue at 100 degrees C with no temperature increase until all of the liquid has converted to gas. And at this point here, we'll have pure gas, and the gas will begin to heat up. So this region here is pure gas. So let's look at this question here. It says, does water increase in temperature during phase changes? Well, notice here, as we're going from the solid to the liquid phase, that the water continues to stay at 0 degrees C until all of the ice is melted. Think about it during the summertime. If you're drinking a Coke and you've got ice in that Coke stays nice and chilly even though the ice is melting. So when you're going through a phase change, your energy is going into changing the phases, not changing the temperature. Once you've changed completely over to the liquid, then you're going to see an increase in kinetic energy. The molecules are moving faster and faster and faster and faster. When they get to this point, now you have 100%, or it's as hot as it can go, so it's at 100 degrees Celsius. Now you're going to start changing over to the gas phase. So when you are boiling your water, let's say to make pasta or to make a boiled egg, the entire time that you have water boiling in that pot, that water in the pot stays at 100 degrees Celsius. It does not get any warmer. Only when you have pure steam left can you begin to warm up the steam and actually make the steam warmer than 100 degrees Celsius. Here's an animation that shows a heating curve, and you'll notice here we've got pure solid. Notice when you've got these sloped regions here that you can use the Q equals MC delta T line. At these straight regions, this is where we're not heating, or we are heating, but the temperature is not increasing at all. We're going to get to this. This is where you've got something called the change in the heat of the fusion, so delta H fusion. Now we have a slanted region with a slope. Again, we can use the Q equals MC delta T. When we're changing phases, we do not see a temperature change. And then again, at the slanted region, we can use the Q equals MC delta T. Let's take a look at what's going on at the molecular level. Here, you have pure solid, so all of the molecules are locked into position. Here you have a mixture of solid and liquid. Here you have pure liquid. Here you've got a mixture of liquid and gas, and now you are completely in the gas phase.